is Sergio Suarez. I'm an Android engineer at FARFETCH. Welcome to another episode of FARFETCH MOBCAST, a series of videos to share our findings with the mobile community. With me today is Hugo.
Hello everyone, my name is Hugo Rodrigues. I'm also an Android engineer at FARFETCH. In this episode, we'll talk about UI testing in Android, the challenges it brings us, and our approach to automate it. Quality assurance has always been a priority at FARFETCH, and there's a continuous effort in improving our testing methodologies and resources to ensure that each release of our mobile apps runs smoothly and bug-free. Unit testing is fundamental to test isolated parts of the app's logic, identifying problems early on, and to prevent bugs from being introduced as new features are developed. But when it comes to validating user experience and making sure that the user interface works smoothly, different strategies are needed. Our quality assurance teams periodically run manual regression tests in our iOS and Android apps before each release to guarantee that new features work as expected and that existing functionality remains unaffected. These manual, regular tests are extremely time-consuming and they require significant human resources. On top of this, they mostly consist in performing a set of steps and validating the results, which is exactly the type of task that could and should be automated.
This is where automated UI tests or functional tests can be very valuable. Once properly set up, these tests can execute autonomously on any device or emulator, browse through apps, screens, and UI elements the same way a user would, and validate what is presented with each interaction. The Android SDK provides a set of tools for writing UI tests, but these require a deep understanding of implementation details, which means only the engineers developing the app are able to write these tests. But ideally, testers should be the ones creating, implementing, and maintaining such tests. So there is a clear gap in the toolchain with a negative impact in our delivery process. In this episode, we will talk about our UI testing framework, a tool based on the robot pattern that we have been working on in order to facilitate functional testing and bridge the existing gap between developers and testers.
Traditionally, UI tests are tightly coupled with the views and the UI components used. They interact directly with them. This means that the person who writes the test has to be aware of the structure of the views involved, the component names, and how they interact with each other.
Robots stand between the views and UI test definitions. Implementation details are encapsulated by this framework, and each robot class only exposes the relevant instructions in a user-friendly way. The idea is to enable anyone to write a UI test with little or no knowledge of the technical implementation details. The robot layer is a set of classes that encode the high-level assertions or actions that we want to take on a view or any other component, encapsulating the logic behind the scenes. The test layer contains the sequence of interactions and validations required for each UI test, written in a simplified manner, as if you were defining a to-do list.
Okay, so let's look at a specific example to better illustrate these interactions. As part of the onboarding process of the FARFETCH app, users are presented with a gender selection screen where they can choose between multiple options. This choice is then persisted within the app preferences, becoming accessible from the user's profile screen, and it will determine basic search results when navigating through the app. Now, let's get a bit more technical. Sergio will write a simple robot class, and then we'll see what a UI test looks like for this particular screen.
We'll start by creating a file for our robot and writing an accessor function. Once the basic structure is written, we'll find the robot class, /genderRobot, and a function that enables the access to the genderRobot methods. /gender, it takes a lambda as a parameter, which is executed within the genderRobot context. It is important to mention that we'll use a set of utility methods that encapsulates the Expressos framework. This is our implementation, but it's not mandatory for your specific project. So we can now start writing the robot class for our gender screen. The initial condition for this robot is that the screen is visible. We are checking that on the init block. We are using its displayed function that takes a view ID and check if it exists on the layout hierarchy. Then we expose possible operations for this particular screen. We'll implement select woman. Behind the scenes, this triggers a tap on a button with a specific ID, but whoever writes the test doesn't need to know that, only that they can select the gender. Finally, we will specify the validations that can be performed after our test is executed. We'll write a result robot class. and it will contain the method isGenderWoman_stored. This method validates if the selection was effectively stored as a result of the actions performed. If not, it returns an exception and our test will fail. So here we are checking if the application gender is woman. After this, we will create an infix function result that allows testers to invoke result robot and check the final state of the test. Now that we have completed the robot, let's see how it could be used to write an actual UI test.
Now the structure of a UI test that uses this robot is really simple. We'll start by creating our test class. We'll call it /gender_test. And it will inherit from our base test and use start activity. We need to initialize activity rule. And we can now start writing our test method. We'll annotate it with @test as with any other test. And within here we can now invoke our robot. We do that by calling /gender. And within this context we can give it instructions to perform. We'll tell it we want to select women. And as a result of that, we expect the correct gender to be stored. And just like that, I've written a test that runs the app, it waits for the correct screen to show, makes my selection, and verifies that it had the intended result. All of this by essentially describing what needs to be done in a very simple syntax. No view code is involved. And when the test is executed, this is the result. We've shown here just one example of a UI test, but the same robot allows as many test scenarios as required, and it can be as complex as we need it to be.
Adopting Kotlin to build the platform has greatly simplified both the robot definition done by engineers and the syntax used by testers to write UI tests. Kotlin functions make it easier to reuse logic, requiring little effort to scale and expand these tests to other screens. So, looking at this example, the navigate_to variable provides access to our navigation context. Overloading operator function -sign enables the specifying context within navigation, home tab in this example. The function after then is executed within the home context. As a bonus, we follow the described structure for deep linking testing. For every intent received, we are capable of testing multiple conditions within the link's landing screen through Lambda accessibility.
Having such a framework available to create automated tests brings important improvements to our testing process. Firstly, it provides the separation of concerns needed in order to create a test without worrying about the logic behind it. It does require input and some degree of maintenance from both developers and testers, but it allows each of them to focus on their own respective tasks. In addition, we're offloading repetitive, time-consuming tasks from testers, and with these tests being completely automated, they can be executed any number of times in any device or emulator as part of our release process. This becomes especially relevant in Android, where we know that device fragmentation is a reality.
The robot pattern provides a flexible framework that can be adapted to each project requirement. The approach that makes more sense for us is to have most robots focused on individual screens of the app. A robot for search, one for bug, one for wishlist, and so on. But a robot can be targeted at anything, depending on your project structure. We have some activity-oriented ones that include several parts of the app, and we use them to test navigation, deep links, and to validate analytic events. For instance, to test analytics, we execute a Gradle script in which a specified UI test runs as many times as we want, and later we check the data sent to our debug environment.
We have also opted for running our tests in conditions that are close to real-world usage, and we do this by using actual network calls and keeping mock behavior to a minimum. While a controlled, predictable, self-contained environment is key for unit testing, We believe that UI tests yield better results when they behave like real users in the actual production environment. This has the downside of slower, somewhat less predictable tests, but it lets us catch more of the real problems that our users are facing. So although there is no single approach to UI testing that's going to suit all projects, we've shown you here a sneak peek at a solution that's been serving us well so far. We hope you found this video useful, that you're able to reuse some of the concepts and ideas presented here in your own projects. Happy testing and stay tuned for more MOBCAST episodes. Bye.
Bye.